Hi, and welcome back to Codex. Our speaker today is Professor Eric Weber from Iowa State University. Professor Weber earned his PhD from the University of Colorado Boulder in 1999 under the direction of Larry Baggett. He did his postdoc at Texas A&M and was assistant professor at the University of Wyoming before coming to Iowa State, where he is now full professor. Professor Weber's research focuses on harmonic analysis and data science with special interests in frame theory, inverse problems, and harmonic analysis on fractals. His publication list includes the influential book Frames for Undergraduates, which is available for purchase at the AMS bookstore. Hint, hint. We are pleased to welcome him here today to tell us about his recent work on phase retrieval. Please take it away, Eric.
Thanks, Joey. Thanks for that wonderful introduction. And thanks to all four organizers for the invitation to speak and for changing the time for me. I teach at the normal time of the Codex seminar. So I appreciate all of you attending at this non-standard time. So I want to talk about conjugate phase retrieval in the Paley-Wiener space. Let me start, excuse me, hang on just a second. There we go. Let me start by acknowledging a few people. So first is my collaborators on this project, Conjugate Lai from San Francisco State University and Friedrich Littmann from North Dakota State University. And I gratefully acknowledge support from the NSF. Okay, so what is the phase retrieval problem? So the way I'll formulate the phase retrieval problem is this. Suppose we have a signal f, an unknown signal f, and we want to reconstruct the signal from magnitudes of linear measurements. So this is an ill-posed problem because a function or signal f and its any unimodular scalar times that signal f cannot be distinguished from magnitudes of linear measurements, but up to only that ambiguity can I reconstruct f from these magnitudes of linear measurements. So to formalize this problem, suppose we have a signal space H. For me, that's a Hilbert space. And we define an equivalence relation on the signal space by saying two signals are equivalent if they are unimodular scalars of each other. And then we look at the following mapping. So I want to map the Hilbert space, the signal space modded out by this equivalence relation into some sequence space. For me, it'll be L2, given by I map the signal f into the magnitudes of these linear measurements. So the phi sub n's are linear functionals on the signal space H. And instead of knowing the values of the linear functionals of f, I know the magnitudes of the linear functionals applied to f. And I ask whether this mapping is injective. Once I mod out by the equivalence relation, I want this mapping to be injective. And if so, then the obvious question is how do I invert this, this mapping? Now, of course, this mapping is not linear, so it's a non-linear inversion process. And I'll say more about that here in a few moments. So this is the way I've formulated the phase retrieval problem. There are several various versions of the phase retrieval problem, but I think this is a pretty broad way to describe it. Okay, so what is conjugate phase retrieval then? Well, suppose our signal space has the property that if you have a signal in the space, then you can conjugate it and you get another signal in the signal space. So for example, Euclidean space, complex Euclidean space, if you conjugate the entries of a vector, you get another vector. Or as we'll see shortly, the Paley-Wiener space, which is a common space used to model signals. That turns out you can interpret it as being closed under conjugation, as I'll explain in a few moments. So now the conjugate phase retrieval problem is, suppose I either can't or I don't care about disambiguating a signal from its conjugate. So this probably has a longer history than what I'm saying here, but this was formulated explicitly by my co-author Conjugate Lai and one of his students, Evans, just a few years ago. So the problem is, again, I want to reconstruct an unknown signal f from magnitudes of linear measurements, where now the ambiguity is both a unimodular scalar and conjugation. So I won't be able to distinguish necessarily between f and f conjugate. So to formally define this, just as before, I define an equivalence relation on the signal space. Now two signals are equivalent if they are either unimodular scalars of each other or they're unimodular scalars of each other together with a conjugation. And then we do the same thing. We consider a mapping from the signal space modulo this equivalence relation into a sequence space. We want to know whether this mapping is injective. Again, we have linear functionals here. And if this is injective, then how can we invert? How can we reconstruct? So by reconstruct, what I mean actually is given the magnitudes of the linear function, the values of the linear functionals on a signal f, I want to reconstruct a representative of the equivalence class of f. So that's what I mean by reconstruct, right? I cannot reconstruct f uniquely, but I can hope to reconstruct a representative of its equivalence class. So that's what I mean by reconstruct here. Okay, so the Paley-Wiener space, as I mentioned, this is a common space for modeling signals. It's very, very common in signal processing. And if you know harmonic analysis, Roy analysis, this is old hat for you, but the Paley-Wiener space has a parameter beta, that's the bandwidth. And we denote by PW sub beta, the set of functions in L2 of R whose Fourier transform vanishes outside the interval from minus beta to beta. So we would say it's a band-limited function or a band-limited signal with band limit beta is another way to say this. And conjugation here in the Paley-Wiener space is actually a double conjugate. So if you take a function in the Paley-Wiener space, it's actually an entire function by the Paley-Wiener theorem. And so you can take that entire function f and map it to what I'll denote by f sharp. So you conjugate the argument z and then you conjugate f. So that is an involution on the Paley-Wiener space. And if we are thinking of our signals as actually the restriction of these entire functions onto the real line, then on the real axis, if you have a signal in the Paley-Wiener space, you can conjugate on the real axis and get another signal in the Paley-Wiener space. So from now on, when we're talking about the Paley-Wiener space, our equivalence relation is actually either f is a unimodular scalar of g or f is a unimodular scalar of g sharp. Okay, so this is the space that I want to try to accomplish this conjugate phase retrieval problem. Now, why is this a problem? So my goal here is to design what I'll call a sampling regime. So I want to design these linear functionals on the Paley-Wiener space such that this sequence of linear functionals does conjugate phase retrieval. And what I mean by that is this mapping A from Paley-Wiener space modulo the equivalence relation to L2 of the index set. I want that mapping to be injective. So that's what I mean by does conjugate phase retrieval. And on top of that, I want to actually have a method of doing the reconstruction. So that's actually a two-part problem, as we'll see here in a few moments. And preferably, I want the sampling regime to actually occur on the real axis. So now why is that? Well, I mean, that's just my own personal preference, but the way I think of this, again, is I think of a signal in the Paley-Wiener space as a function on the real axis. I mean, if you think about, for example, an audio signal, that's a signal of time, a single variable time, real variable time. And I don't want to have to try to sample, as it were, off the time axis. So that's not to say that that can't be done. It's just this is sort of the physical interpretation of why I want to do this. I'll say more about that in a few moments as well. So I want to design this sampling regime that these two things happen. And the interesting thing about the Paley-Wiener space, or actually entire functions in general, is that if you know the magnitude of the entire function on the real axis, that does not determine the entire function everywhere, even up to unimodular scalar. So for example, in the Paley-Wiener space, if you have a signal whose Fourier transform is supported on an interval that's strictly smaller than minus beta to beta, then you can shift in the Fourier domain, and that causes a modulation in the time domain or spatial domain. And so you have two signals that are completely different as far as this equivalence relation is concerned, but their magnitudes on the entire real axis are the same. So it has to be more than just knowing the magnitudes of this unknown signal on the entire real axis. So as I'll mention here in a few moments, one way to do this is actually go off the real axis if you happen to know information about the magnitudes off the real axis that can actually help you reconstruct the unknown signal F. So to put this into context, here's a very short history of phase retrieval. I think the phase retrieval problem actually goes back to X-ray crystallography, probably in the 40s, if not before. But from a numerical perspective, I would say the first paper on this was the Gerchberg-Saxton paper from '72. There they introduce a reconstruction technique, which is called an alternating projection method, which we will use actually in our solution here. Philip Rosenblatt, Levi-Stark, I'm not sure how to say Levi or Levi, but Levi-Stark actually proved some rigorous results about the alternating projection method of Gerchberg-Saxton that I'll mention here also. This also appears in inverse spectral theory. So my colleague Paul Sachs has written a number of papers on this, at least as early as the 90s, on the use of the appearance of the phase retrieval problem in inverse spectral theory. The quote-unquote modern view of phase retrieval is probably within the viewpoint of frames. This was introduced by Radu Balan and Pete Kazaza and Dan Edenen in 2006. And I have a couple of papers listed here. There's probably thousands of papers that have come out since then. So this is an extremely short list here, but again, that's probably the more modern view of phase retrieval. There are many reconstruction techniques, and this also is not an exhaustive list by any means. The alternating projections method, as I mentioned, the Gerchberg-Saxton method. We have various methods that are based off optimization problems or semi-definite programming, of course, largely led by Candes. My favorite method is the Kaczmar's method for doing phase retrieval, simply because I really like the Kaczmar's method, but I actually don't use that for phase retrieval myself. And then what about phase retrieval in the Paley-Wiener space itself? So there was a paper almost 10 years ago by Thakur, and then another paper a few years later by Paul, Yang, and Bosch. Again, I'm sure I'm not saying those names correctly. I apologize for that. Thakur considers the Paley-Wiener space, the phase retrieval problem in the Paley-Wiener space, but only with real valued signals. So in this case, the ambiguity is only ±1. And he proves a reconstruction method. It turns out that in this case, he actually goes off the real axis to do the reconstruction. He has to actually move far enough off the real axis so that he knows that there aren't any zeros. Those of you that are familiar with phase retrieval, you know that zeros always cause a big problem, right? Because zero doesn't have a phase. And that's going to be a problem for us as well that I will discuss at that time, that we too are going to have to avoid zeros in order to do our reconstruction. And then Paul, Yang, and Bosch, they consider the full phase retrieval problem in the full Paley-Wiener space. And what they do is they design what they call structured modulations or structured convolutions. So what they do is they design linear functionals that are samples of the function. They're actually linear combinations of samples of the function where they actually sample off the real axis. So they have a sampling, it's not a grid, but they have a sampling scheme where the samples are distributed both along the real axis and along several horizontal lines off the real axis. And they consider linear combinations of these samples. And then given the magnitudes of those linear combinations of those samples, they come up with a reconstruction method. And their reconstruction method actually occurs in the Fourier domain, not in the spatial domain. But this is where we get our idea for using these so-called structured modulations or structured convolutions. Now there's an even shorter history of conjugate phase retrieval. The first paper that we are aware of in which there is anything related to what we would call the conjugate phase retrieval was a paper in 2004 that appeared in Journal of Fourier Analysis and Applications by McDonald. And what he proved is that if you have two signals in the Paley-Wiener space, if their magnitudes are equal on the real axis, and if you have a second copy of it, either like a blurred copy, which is a difference of shifts, or if you have access to the derivative, so that's actually a more recent phenomenon, sampling the derivative of a signal. But if you have access to the derivatives, if they have the same magnitude as well, then these two signals are equivalent up to, again, the equivalence class is unimodular scalars and also conjugation. So he didn't call it conjugate phase retrieval at the time, but it's not really phase retrieval in the classic sense because his theorems, you cannot disambiguate F from its conjugate. But that's the first time that we've seen in the literature that that idea is considered. And then, as I mentioned, my co-author Conjugate wrote a paper a few years ago with his student discussing conjugate phase retrieval in finite dimensions. So this is just a representative example of a result that they have, which is if you have three vectors in R2, then those three vectors do conjugate phase retrieval in two-dimensional complex space if and only if the determinant of a particular matrix is non-zero. So they have this in 2 dimensions, they have this in 3 dimensions, they have the analog of this theorem in 3 dimensions. They didn't extend from there. But the idea here is, suppose you want to do phase retrieval in complex space, but for some reason or another, your vectors, if you think of them in terms of frames, your frame vectors are real vectors. Then there's no way of distinguishing from the magnitudes of the inner products. There's no way of distinguishing a vector in CD from its conjugate, because if the sampling vectors or the inner product vectors, the frame vectors are real, then the inner products and the conjugates of the real products have the same magnitude. All right, so this is a short history of conjugate phase retrieval. So the conjugate phase retrieval problem, I'll shorthand the CPR, is strictly weaker than phase retrieval because there are vectors, namely real vectors in CD that do conjugate phase retrieval but do not do phase retrieval. So one interesting question that we've thought a little bit about, but not a lot, is how many vectors can you get away with? So it's known that in real space, in RD, you can accomplish phase retrieval with, I don't remember exactly the number, 2D minus 1 or 2D minus 2, I forget exactly, but on the order of twice the dimension, that's the number of vectors you need. In complex space, it's 4D minus 4, as I recall, so on the order of 4D. We're wondering if in the conjugate phase retrieval context, if you can get away with 3D or much smaller, at least much smaller than 4D vectors. We don't know the answer to that question. It turns out that we do not know of a proven reconstruction method for conjugate phase retrieval. We will use the Gerchberg-Saxton method, the alternating projection method. Now that cannot be proven to work. It's actually known to not work in general, but we show that experimentally it works pretty well. And then, can conjugate phase retrieval be made robust to noise? So this is an active area of research for the phase retrieval problem. It would make sense to ask the same question for conjugate phase retrieval. Okay, so what is this alternating projection method? So suppose we have a matrix A, so we might call that a sensing matrix. It's not compressed sensing, but that's what it might be called. Or if you want to think about frame vectors, the columns of A are the frame vectors. So suppose I take a signal V and I take the inner products with the column vectors of A, and then I take the magnitudes of those inner products. I want to reconstruct a vector from the equivalence class of the signal V. So here's what I'm going to do. I'm going to choose phases. So I'm going to choose unimodular scalars lambda 1 to lambda n. What I'm going to do is I'm going to take the magnitudes of the measurements that I have, and I'm going to stick these random phases in front, right? I don't know the phases. I'm going to just randomly pick phases. And then I'm going to apply the Moore-Penrose inverse of A transpose to this vector. And what I get out is I get out an estimate for W. It's not going to be in general a representative of the equivalence relation for the vector V, but it's an estimate. So that's the first projection. And then what I do after I've obtained this estimate W, I'm going to renormalize the samples of this estimate W with my vectors by taking in other words, I'm using the vector W to estimate the actual phases of the measurements that I'm missing. That's the second projection. This is a nonlinear projection. I'm projecting onto the set of vectors that have the same magnitudes as the original measurements. So this is the alternating projection. I have a linear projection given by the Moore-Penrose inverse, and then I have a second nonlinear projection by projecting onto the set of vectors of the same magnitude. And then I repeat this process. And this is this alternating projection method. This is what Gerchberg and Saxton introduced. And as I said, it's often called the alternating projection method. And what we observed when we were using this on our set of vectors that do conjugate phase retrieval is that this method actually does converge. That's actually proven by Levy-Stark, the Levy-Stark paper. If you have to interpret their results carefully, but this is what happens. It doesn't have to converge to a solution, though. That's the problem. That's why it doesn't. We can't prove that it actually does a reconstruction, is because it converges, but it doesn't necessarily converge to the right thing. It depends on how you see the original phases, which is why we just do random. So this is called a trap in the classical phase theory, phase retrieval literature. We also actually observe numerically these traps and tunnels. That's another thing that's referred to. So our reconstruction actually failed often, but you just try again by reseeding the unknown phases. You pick random phases to start with. You see if you get a good reconstruction. If not, you start again with a different selection of random phases at the beginning. And for a particular matrix that we used, which was a 3×6 matrix, the reconstruction error was on the order of 10 to the -4 after only 400 iterations for roughly 80% of the instances. So this was sufficient for our purposes to use this method to do these reconstructions. So again, not proven a reconstruction, but experimentally it seems to work. It certainly works well enough for our purposes. Okay, so back to conjugate phase retrieval in the Paley-Wiener space. So we get an immediate corollary of the results from McDonald. And just to put this into context, if you have a signal in the Paley-Wiener space, its derivative is also a signal in the Paley-Wiener space. That's easy to see. If you take a signal and multiply by its sharp, you get a signal with twice the bandwidth. And if you take a signal, the derivative of a signal and multiply by its sharp, you also get a signal of twice the bandwidth. So an immediate corollary of McDonald's result says that if you have a set of sampling for the Paley-Wiener space of twice the bandwidth, so that means you have a sequence of points along the real axis for which you can do reconstruction using something analogous to the Shannon sampling theorem. Then if you sample the function at this set of sampling and then take the magnitudes of those samples, and you take a shifted or blurred copy of the signal, so f shifted by b minus f, and you sample that function at this set of sampling and take the magnitudes of those, then the mapping from the Paley-Wiener space modulo the equivalence relation to the sequence of magnitudes here is in fact 1-to-1. And similarly, if you sample the derivative of the signal and take the magnitudes of that together with the magnitudes of f sampled at the set of sampling, that transformation, that mapping is 1-to-1 as well. So this is an immediate consequence of McDonald's theorem together with the lemma. The problem here is just because these mappings are 1-to-1 doesn't mean that we actually can invert them in a numerical method. In particular, if you try to do that, here's what happens. So we can reconstruct both f squared and the blurred copy of f squared on the real axis everywhere because we've sampled sufficiently fast. But just because you know those magnitudes doesn't mean that you can get a representative of the signal back again, because the way McDonald does this is using complex analysis. In fact, you need to use the Weierstrass factorization of the unknown signal f, which means you need to know where the zeros are. And numerically speaking, I think that's not really a viable method. There may be some disagreement with that, but from my perspective, trying to find the zeros off the real axis of a signal is a very difficult problem. Okay, so I don't think of that as being a viable reconstruction method. And on top of that, this inversion is unstable. And that's not just simply because we're not clever enough. So Mallah and Waldsberger observed that this inversion was unstable in their phase retrieval problem paper. And Cahill, Kazaza, and Dobeshi's prove explicitly that the phase retrieval problem is unstable in infinite dimensions. So we have that problem working against us as well. But we're not going to let that deter us. We're going to propose a sampling and reconstruction method following the Paul-Yang-Bosch idea of using structured convolutions. All right, so what does this look like? So I need multiple copies of my signal that have been, you might think of it as blurred, or you can think of it in another way. The way I think of it is you take the signal f and you convolve it with a linear combination of Dirac masses. And the data I'm gonna have access to are these blurred copies of the signal f sampled at some sequence of points on the real axis, and then the magnitudes of those samples. So that's the data I have access to, and I wanna reconstruct, again, f. And so I need to design the set of points that I'm going to sample at, and I need to design the structured convolutions. I need to come up with the coefficients and the locations of the Dirac masses, if you want to think of it that way. I need to specify all three of these quantities here in order to specify my sampling regime. Okay, so the coefficients of the linear combinations are going to come from this matrix A that I want to design so that it does conjugate phase retrieval in k-dimensional complex space. So I choose such a matrix A, and those are going to be my coefficients. In general, the entries of this matrix are going to be real, but just in case they're not real, then notice I have a conjugation there on the convolution. I'm going to choose my sampling points to be a set of sampling for twice the bandwidth. So I've simplified things here by specifying pi as my bandwidth. So I want to pick my set of sampling points to be a set of sampling for the Paley-Wiener space of bandwidth 2 pi. And then I want my shifts, so I've got shifted copies of my signal in this structured convolution. I want to choose my shifts. So I'm going to choose them to be real, which is different than the Pol-Yang-Bosch method. They choose the shifts to be complex numbers, so you're shifting off of the real axis. We're going to stay on the real axis here. And I need those shifts to have the property that if I look at the lattice generated by them, the integer lattice, I need finite upper barreling density and I need lower barreling density greater than 1. So I need to pick all of these parameters that satisfy these conditions. And if I do pick them this way, then the sampling scheme does conjugate phase retrieval, which means that the mapping that I've been referring to as A, that mapping is in fact injective. Now the trick is going to be the inversion. So how do we do inversion? Well, for this, for convenience for myself, I'm going to actually choose my shifts, my B sub j, to actually be on a lattice themselves. And so I choose them to be j over b, capital B, for some integer capital B. And now here's what I'm going to do. So remember, let me scroll back here, or at the top of the screen there. What I have access to are these convoluted copies of my signal f, sampled at the points t sub n, and then the magnitudes of those. That's what I have access to. And so I can use those samples to actually reconstruct the convoluted copies of the signal on the entire real axis. I can reconstruct that just by using the Shannon sampling theorem, or the analog of the Shannon sampling theorem if my t sub n's are irregularly spaced, for example. So I reconstruct the convoluted copies of my signal f everywhere on the real axis. And then I'm going to choose a beta. And this is what I said before, where I need to avoid zeros of my signals. So I'm going to choose a beta at random. And because my zeros of all of these signals, all the convoluted copies of these signals, because that set is countable, I can choose a beta at random, and with probability 1, I'm never going to hit a 0 in what I do next. So I choose this beta at random, and then I know that with probability 1, I know that I'm not going to run into a problem with zeros. So I have the convoluted copies of the signal f on the entire real axis. So now what I do is I resample those convoluted copies of f, but now at points that are very useful for me, which is a lattice again, divided by, so the integer lattice divided by this integer b, and then shifted by the beta so that I don't encounter any zeros. So none of those resamples are gonna be 0 in magnitude. And then what I'm going to do is I'm going to group these samples together into k consecutive samples, and I'm going to do phase retrieval, conjugate phase retrieval using the matrix A. So this is where the alternating projection method comes in. I'm going to group these samples together so that it can use the alternating projection method to reconstruct the samples with phase, but just in small groups. Okay, so I'm going to have these groups of samples of my unknown function f with phase, but I don't know the global phase, and I don't know whether I need to conjugate or not. So I have samples for every integer n. I'm going to have these collection of samples that I've reconstructed the phase except with a global phase factor, but the global phase factor depends on the n. And I also have the ambiguity of conjugation, which depends on the n. So now what I want to do is I want to stitch these samples together. So I've chosen my resampled values of these copies of f in such a way that the sample grouping for n and the sample grouping for n plus 1, they have overlaps. They have at least 2 overlaps, and none of them are 0. And so what I can do is I can stitch them together by choosing a phase and a conjugation so that they're consistent with each other. So I have a group of samples for n. I have a group of samples for n plus 1. And for n plus 1, I re-choose a phase, a global phase, and I re-choose a conjugation so that they are consistent with each other. And then I repeat for n plus 1 and n plus 2, and n plus 2 and n plus 3, and so on and so forth. So I'm stitching them together so that I get a global phase factor and a global choice of conjugation that are all consistent. So that's what I say there. And then what I end up with after this process is done is I end up with the values of my unknown signal f at these sample points, this integer lattice, up to an unknown phase factor lambda, and up to I don't know whether I've conjugated in this process or not. I may have picked the wrong choice of conjugation. But up to those 2 ambiguities, I have exactly the function values at this lattice points, and now I can reconstruct using the Shannon sampling theorem again. So again, I'm reconstructing from the magnitudes of the samples. I'm reconstructing the phases locally, and then I'm stitching them together to get the global phase and global conjugation. And notice I don't have to leave the real axis to do this. All right, so we did a number of numerical examples of this. So here's one of them. So here's what I did. To construct a generic function in the Paley-Wiener space, I just chose 20 random complex values for the function at the integer minus 20 to 20. I set f of 0 to be 0, so I know that I do have to shift away from the integer lattice because I forced one of the function values to be 0 at 0. Here's our sensing matrix that we choose, this 3 by 6 sensing matrix. This actually does conjugate phase retrieval in C3. It does not do phase retrieval in C3, but it does conjugate phase retrieval in C3. And I've chosen my shifts to be on the half integer lattice. We're going to sample our convoluted copies of our signal at the half integer lattice. And then again, what I have access to are the magnitudes of the samples of the convoluted copies of f at the half integers. And then I select this random beta. I know I have to shift away from the integer lattice because f at 0 is 0. So I choose a beta at random in MATLAB. And then I reconstruct for n from minus 20 to 20. Actually, I think that should be minus 40 to 40, by the way. I construct half as wide as the original coefficients. Excuse me, twice as wide as the original coefficients. I reconstruct these values squared of the magnitudes of the convoluted copies of f. I group the samplings together, as I mentioned, and I apply the alternating projection method to the magnitudes of these inner products to estimate the phase and conjugation for each value of n from minus 40 to 40. Then I stitch them together. So starting from minus 40, I start stitching them together so that the phase factors and the choice of conjugation are consistent. I actually work left to right to do this. And then I reconstruct, once I've chosen that global phase factor and that global choice of conjugation, I reconstruct f from those samples. And here's a graph of our reconstruction. The real part is on the left, the imaginary part is on the right. We estimate the reconstruction error using the Frobenius norm. It's on the order of 2.6% error. The beta that we chose using MATLAB's RAND command was 0.2119. And it should be noted that the choice of beta actually does affect the reconstruction error. So I'll get back to that in just a moment. So here's an expanded view of the real part of this reconstruction. just so you can see it better. As I said, the choice of beta matters. So here is a graph that shows what happens if you apply the Gerchberg-Saxton method, and of course that fails sometimes. So if you use the wrong choice of seeding and you don't reseed, if you make the wrong choice of phase and conjugation, then you start seeing errors propagate. So as I said, I'm working left to right. So as you see, I have good reconstruction starting at the left, but then at some point an error occurs in my reconstruction and now the errors propagate. So the choice of beta affects the reconstruction error, because if I choose a beta for which my samples are very small in magnitude, then the phase is of course much more susceptible to errors when I have a small magnitude. And so errors propagate in the way I'm doing the reconstruction from left to right. So this is an artifact both of our reconstruction method, but also because we're in infinite dimensions, the inversion is going to be unstable. As I said previously, it was proven that it will be unstable. Okay, so this is how the choice of beta actually can affect the reconstruction accuracy. All right, and one last thing to mention, I talked about towards the beginning that that there's this interesting question of how many vectors do you need to do conjugate phase retrieval in d-dimensional complex space. We don't know if 3D is the right conjecture. I wouldn't call it a conjecture. I would just call it a fun guess that three times the dimension is the right number of vectors. We have no idea. But here's some slight evidence that that's the case. So if you look at the McDonald theorem and our corollary of it, we actually sample 2 copies of the signal at twice the Nyquist rate in the Paley-Wiener space. And so the sample complexity is 4 times the Nyquist rate. So in other words, this is infinite dimension, but the Nyquist rate is how you would measure redundancy here. We're sampling at 4 times redundancy in the Paley-Wiener space. With our reconstruction method, we actually have to sample 6 times the Nyquist rate because we need 3 copies of the unknown signal. That we're sampling 3 copies of the unknown signal at twice the Nyquist rate. So we need to increase the redundancy for our reconstruction method. But if we allow ourselves to cheat and say, I'm only going to try to reconstruct generic signals, not all signals, but only generic signals, and by generic I mean an open dense set, we can actually reduce the sample complexity to 3 times the Nyquist rate. And we do this by simply sampling 3 copies of the unknown signal f at the integer lattice. So that's 1 times the Nyquist rate. So I have 3 copies of f, but sampled at 1 times the Nyquist rate. And I can, if it's a quote generic signal, meaning it has no zeros at any of the integers, then I actually can do the reconstruction here. I can do the conjugate phase retrieval reconstruction. So again, that's not all signals, right? Any signal that has a 0 at one of the integers, this will definitely not work. But again, for generic signals, we can reduce the sample complexity to 3 times the Nyquist rate, redundancy of 3. I mentioned a couple of lemmas here earlier in the reconstruction method. So here's the lemmas. It regards this choice of beta. I want to avoid the zeros. I also want to avoid the idea that sometimes if I have a finite collection of samples of my signal f, or in this case, the statement of the lemma is g, if I take a vector of those finite number of signals and I take the conjugate of those, I don't want those to be collinear, because that can cause a problem with whether I can select when I'm pasting together the phases and the choice of conjugation. That can cause a problem if these two vectors are collinear, then I don't know whether I need to conjugate or not. And that will cause errors later on to propagate. Well, fortunately, the only the times that those vectors are collinear, the vector of some finite set of samples of this entire function g and the conjugate, those are collinear either everywhere on the real axis, in which case I don't actually have to worry about choosing my conjugation incorrectly, because either choice will work, or that happens at most countably many points. So now I'm back to choosing my beta again and avoiding a countable number of points, both the zeros of my signals and the points at which these vectors are collinear. And I can avoid that by choosing beta randomly, and I know with probability 1 I don't fall into that trap. All right, that finishes my talk. Here's a list of references, and I thank you very much for your attention. Now we open the floor to questions.